Okay, I'm Imam Linar from University of Ljubljana, and I will represent Team Slovenia. I will present problem number 7 about wavy pages. Kako se to naprej da? So the problem statement was, after extensive use of a book, wavy bands may form in stacked paper. Investigate the shape and the distribution of bands. So at first we ask ourselves, where do those waves actually form? We found out that those waves form only in hardcover books. And then we were further interested in whether on which edges of book those waves are formed. We know that paper is made of fibers and that those fibers are oriented in some direction. So let's see whether those direction matters. We wet a line along short edge of paper and along long edge, and we expected both to become wavy. As you can see, only a line along short edge became wavy. So we suppose that that orientation of fibers does matter. So, and this is also what we can see in books. Waves form only at upper edge and at bottom edge, but not at side edge. And if they form at side edge, they don't form at bottom and upper edge. Here, pink color represents upper edge and blue color represents bottom edge. And as you can see, normally wavelengths at upper edge are longer than waves at bottom edge. And what you can also see from this graph is that there exists a relation between wavelength of a book and thickness of a book that seems to be linear for short books, for thin books. So we decided to fit power function. However, we logarithmized it for easier fit, and we got power b to be 1. So that implies that there is a linear relationship between wavelength and thickness of a book, what we also supposed. There is not only a relationship between thickness of a book and wavelength, but also between thickness of a wet part. As you can see in these two photos, when only thinner part of book is wet, shorter wavelengths are formed. And then we asked what was the reason for this phenomenon, in fact. We read some really old magazines, and what we found was that the shape and the distribution of waves in these magazines were just exactly the same as waves found in old books in library. So we suppose that the major cause of this phenomenon is dampness. But dampness can in fact influence in 2 ways. We know that there are some random irregularities and tensions in material already from factory. And another explanation is that fibers swell and thus paper extends, and this causes wrinkling. And we also expect factors like thickness of a book and material of paper to influence. So let's see whether random irregularities can explain this phenomenon. We know that some hills and walls appear if you dry a wet paper. But in fact, we found out that curvature found in some books can be much greater than curvature of those hills and valleys. So this explanation seems not to suffice the phenomenon. So luckily we have another explanation. So this is the extension of wet fibers. We will suppose that this extension is constant, so that it always extends for delta alpha. So our goal was to squeeze a curve of length L into a box of length alpha. And we wanted to find such a curve so that curvature would be minimal. And we used Euler-Lagrange equation and Lagrange multipliers to obtain the solution. And the solution was a sine function with amplitude A and wavelength lambda. And since we were interested in relationship between wavelength and amplitude, we inserted the solution into initial equation. And as we suppose that that we are looking only at points that is true that alpha is much greater than or greater than lambda, it is true that everything is constant except for amplitude and wavelength. So we can see that wavelength is proportional to amplitude. I already mentioned that waves are formed only in hardcover books. So for now, we will assume that those covers of book are fixed. In new book, there is some space between pages, and this space when pages get wet, they stick together, and this distance between pages becomes smaller, only a fraction of previous one. And there appears some extra space that we will denote by 2 times A. And we recognize this 2 times A as amplitude of waves. And as this is just the difference between initial thickness of a book and final thickness of paper, we can see that amplitude is proportional to thickness of a book. And since amplitude is proportional to wavelength, also wavelength is proportional to thickness of a book. And just a remark here that this constant shrinking only for thin books, because it appears that material and thickness of pages is almost the same for all thin books. So let's return to experiments. In experiments, we also got a linear relationship between wavelength and thickness of a book, what I just got already also in theoretical part. And you may also be wondering why we didn't just measure the relationship between amplitude and thickness of a book. On the sketch on the right can explain this. Actually, we found some books where the covers were not at the same distance for the whole book. And we were able to determine the relationship between amplitude and wavelength for this book. And this is also what we've seen in theoretical part. So to conclude, as this has not been obvious at the beginning, it is physics that governs wavy pages. We saw that wavy pages are caused by dampness. This leads to extension, the swelling of fibers, and thus extension of paper. And this results in wrinkling. The waves have the shape of sine, and wavelength is proportional to amplitude. Amplitude and wavelength are proportional to thickness of a book. Waves form only at upper and bottom edge of a hardcover book. And since books are more open at upper edge, also wavelengths are longer at upper edge. We extracted many interesting facts about wavy pages just from measuring books. So think of them next time when you will complain about wet books. Thank you.
Hello, I'm Sahan Huang from School of Physics, Nankai University, and so So this is problem review. I think the web page after the question is that after extensive use of book, wavy bands may form in the stacked paper. Investigate the shape and distribution. And I think the keyword is extensive use and stacked paper shape and distribution. For the first keywords, I think we have the same recognition that the extensive use isn't the master reason for form that web pages is the dampness, right? So I think that is the right source. And for the stacked paper, I think I think it is necessary to state that is there any difference? Is there any difference of single paper and stacked paper? And I think the shape and distribution is to find its wavelength. Okay, so the next page. I think the strong and weak point is that I think what it is doing great is that is you explain where do waves appears is that dampness. Okay. And here's a strong point, and the weak point is that your figures are drawn hasty and you did not clarify the quantities, and it is really rough. And there are only one dimension you think. So the paper is 2D, right? So when you go into the inner part of the paper, and the amplitude is different. When you go inner, and the amplitude is become small, yeah, right? And the gravity, and I think we have discussed this. And next page. So I want some advices that maybe the first is not all the pages have different curve, and it can't be simple. Can be simple. So and one dimension is definitely not enough. And when you calculate the energy of its potential, you have to consider a 2D model. And the fourth advice is that you have to consider the difference between the edge and the inner parts, and you have to consider one page and more papers stacked. So what is the difference? Have you do the experiment? So here is the point we want to discuss. We think is necessary to discuss later. So first is that so whether it is true that one dimension can really represent the two-dimensional model, and okay. So 3 point is that the sine function may be not maybe not correct enough, and you have to do the Fourier transformation and analyze it. So what if it is another function or something else? So, and you want to discuss the edge and the inner parts. So what is the difference? Okay. So here is our represent about opponent.
Thank you, dear opponent. Now we move to the next action, is discussion between a reporter and opponent. So please, the reporter, just share your screen again, because probably there would be questions from the opponent about your presentation, and then ask and then answer the questions that opponent raised in his speech. When you share your screen, I will start the clock. Reporter, Do you hear?
That's what I'm. Okay.
Shall we start?
Okay, so.
Oh,
You can share presentation.
we are prepared. We are prepared.
I'm asking the reporter team.
We are sorry.
No
in
problem.
the middle,
no problem.
Zoom
No
took
problem.
our share
No
screen
problem.
out.
The
We
clock
didn't
is
know.
stopped. No problem. Yeah.
What was the shared screen?
Don't be hurry. It's a message to all. Don't be hurry. It's not a problem. So let's start. I start the clock.
Yes, one second. Okay, so you asked me about whether you say that I considered only one dimension, and that it would be better if I considered two. But I would answer to this question that here I showed that waves are formed only in one direction. So that I think it wouldn't make change if that another dimension doesn't make change because waves form in one direction anyway.
Oh, okay. But what I mean is that when you go deep into the inner part of the paper, the amplitude is smaller, right? But if the decline is not a linear, is not a linear decline, you have to when you calculate the energy potential, maybe you have to consider that because the energy potential is the minimum when the 2D when the 2D for the whole paper is taken the minimum, but not the one dimension is minimum. Yes, is it right?
I mean, yes, it is true that waves are smaller in inner parts of book because normally pages get wet more at outer edges than at inner parts. So yes, in this case, yes.
So maybe my advice is that maybe after you damp the book, you have to open it and you detect its all points and you draw a picture 2D picture for the amplitude of all points and maybe you shouldn't put it into computer and calculate the energy potential. Yes. And so and another thing I want to discuss is that another thing I want to discuss is that I remember that you said the isotropically, so the paper is isotropically or anti-isotropically. You neglected that. But this is based on the one dimension. I think that is right. And if you consider the two-dimensional model, that is inevitable. So this could be very hard when you take two-dimensional model. It will be more complex. And so we can discuss more.
Can you repeat the questions that you had on your presentation for discussion points, please?
Okay. Well, need to. Oh no, you are share the screen, man. I just no, you don't close it. I'll check it. I'll check it again. Oh, okay. So for we discussed before, you neglected that the influence. the influence of gravity, and you think that is nothing different. But in my experiment, I think I found that there really big difference. Well, I don't think I don't know what your experience was set up, and for my experiment, we take two ripples and hand the books up, and we found that the wave shape and distributions are very irregular, and
yes, it can be that, but only if the amplitude for waves is really big. But if it's not, it doesn't really influence. And as you have seen in this graph, we did it for quite a lot of books, and those purple points are almost exactly are distributed almost exactly the same as others, or there are something between pink ones and blue ones.
okay, I think that is
We
reasonable.
also took a representative sample from library. We were measuring like all books that library worker gave us.
Okay. The discussion time is.
So now we move to the general discussion, and members of your teams can raise a hand and ask any question. And any member from the reporter team also can answer.
Is there not a weird quality?
So I would like maybe that the opponent and reporter discuss a bit how they would best measure the two-dimensional profile of the book, because it was quite stressed by the opponent that we should measure the two-dimensional profile, but we would like to know how to do it. Not so that we leave the form in the book.
Our network is bad connected. So are you asking us some questions?
Yes, I was asking both the reporter and the opponent, because it was stressed quite a lot that the model should be two-dimensional, but to confirm that model, we have to do some measurements. And I would like to hear the best proposals on how to measure the two-dimensional profile of the waves in the books, so that it would be important in the scale of error, because there will be some error associated with that.
Okay. I think first we damp the books, right, and we opened it, and we can use a laser, right? We can use a laser to detect the length, right? And for every point, we can use this method. For the time, the laser in and reflected. So this is our thought about how to measure the two-dimensional model.
You can also use streezers to if you but you somehow destroy a book. But if you have some old magazines, you can also do this. You can cut the book and measure the rating.
Yeah. This is a method too. Yeah. But how you can verify that if you cut the book into pieces, you won't influence its distribution and shape of the wavelength?
Well, I would argue that material of book is deformed, is already deformed, and because of dampness, and that it doesn't, if you don't have wet fingers, it doesn't influence much, because it would appear wavy again when you cut it.
Oh, okay, okay, but I think it is still have to discuss more. So.
And you mentioned that I mentioned only sine function that that is the shape of those waves. But in fact, this was we got this this sine function analytically.
So now we run out of time. If you have a short answer, please.
We use Lagrangian so this is how we got this sine function. We were using Lagrange multipliers and Euler-Lagrange equation, and the solution was a sine function. So I guess it's
I have several questions to the presenter team. The first one is you have some L length which you consider to be constant. What is the reason that you consider this L to be constant and not to depend from the coordinates, not to depend from the distance to the book cover?
Actually, I considered it for teen books. It is not true for thick ones, and that's why we don't get such linear relationship for thick books. But it is a good approximation for teen books.
But what are the physical reasons which determine this L? How can one look at the book and think which L should he take?
Actually, if book is thin, it doesn't really matter how far from cover it is, because the distance are quite small, and in fact this thing depends on extension of paper, and the extension of paper and the extensions of paper are almost the same, no matter how wet books are. But because of because curvature is different at different parts of thickness, it is this argument is not true for thick books.
Oh, okay. But what about
I'm sorry, Vladimir, we have another questions from the jury. Alexei, please, your question.
Dear reporter, you were minimizing the energy when writing the Euler's equation, and you obtained a sine wave with basically any wavelength. But do I understand correctly that the sine wave with the longest possible wavelength, the wavelength equal to the width of the book, equal to the length of the book, will have the lowest energy ever because it will have the lowest band over the page?
Yes, but it in fact it is connected to amplitude. If because the book can't the waves can't extend more than free space in that free space that arises is so.
So
there
we
is-
have this physical limitation, which might be, can it be related to how much the book is pressed on the sides and so on?
Actually, here the press of book is important only when books are horizontal. But here we derived it for books that were placed vertically, and we suppose that that those covers are fixed so that pressure force can be neglected.
And for Euler's equation, when deriving it, you assume that the page is fixed on both sides.
Yes.
Why can you assume it?
14 books. It's almost as we can suppose that length of book is like infinity, because errors are quite big, and this is a good approximation.
But can't the more distant edge of the page go?
I'm
up?
sorry, Alexei, we have also a question from the Luis. Luis, please, your question.
Thank you. For both the opponent and the reporter, can you extract from your data what is the difference from a one-dimensional model from the two-dimensional model? Because if you have one-dimensional model, you will have also only the projection of the sine wave from your side. But if you have a two-dimensional model, maybe you can have another projection. Can you extract, what is your opinion for the possibility to extract this difference from your data?
I would say that the projection from edge parts would have maximal amplitude, but I mean, I showed that the extension is mostly in one dimension, and that in second dimension it's almost negligible, and also yes, so that
the opponent
in one dimension, and if there is a difference between two dimensions, it's caused only because edges are normally more wet than the inner parts. But the difference is not great according to our measurements.
Mm-hmm. And opponent, please answer quickly. China team, hello.
Opponent, you.
Hello. So are you asking us to show our data or something else?
No.
Huh?
I'm sorry.
Can you hear me? Can
you
you
hear me?
us?
Can you hear me?
Yes, we hear you.
Okay. So you want us to show our data, or also I didn't hear your question clearly.
The point is that, in particular, you mentioned that you need a two-dimensional model to study this effect. And what am I asking is that if you can extract the difference between one-dimensional model from the two-dimensional model from the data that you gather from your experiment. I mean, if you can get the difference, and you can say, yeah, I need a two-dimensional model because such and such and such. Did you get it?
Okay, because so first we are opponent, and we don't need to show our work, right? And in our work, in fact, we observed that in a two-dimensional, when you go to the inner part, it is not a sine function, or it is not an easy function we can get. Become very difficult to measure that. So I think the one dimension can't replace that 2 dimension. We need a 2-dimensional model.